we will next see how dominance and predecessors of a dominated vertex works out. So what we will show is the following, that if U dominates V, then that is equivalent to U dominating all predecessors of V. We will see that with a figure. So first, terminology. If we have a branch from U to V, then V belongs to the set of successors of U, and U belongs to the set of predecessors of V. So SOC and pred, they are, if there is a direct edge, not a path. Okay, so this is what we want to show, and that's equivalent to U strictly dominating V, and well, and then what I said on the previous slide. So this is the figure that we have. I mean the situation, and we will show this first going in the right direction. So we will assume that U dominates V and show that it then must dominate each predecessor of V. So let's assume falsely that there is a predecessor of V which U does not dominate. Okay, so we can put it here. Whoops, there was some lagging. It doesn't matter very much, but here we have PI. And that's a predecessor of V. And now there is a path which does not include U. Since we assume that U does not dominate PI. But then we have a problem, because now U does not dominate V, which is an assumption, which means that it must be the case that U dominates each predecessor of V. So that is wrong. Okay, and now let's look at in the other direction. Namely, that U dominates each predecessor of V, but it does not dominate V. That means there is a path from S which does not include U to V, but this is impossible, since we have assumed that, okay, there should be another predecessor, or S can be the predecessor, it doesn't matter very much. So here is another predecessor, so since now we have a path which does not include U, then U does not dominate V. But we have already assumed that the U dominates each predecessor. So this cannot be correct either. Instead, we have that if U dominates V, then this is equivalent to U dominating each predecessor of V. We will next see the simple algorithm which makes use of this.